All right, everybody ready? Sorry, I didn't get to class early enough today to get music going, but maybe I'll play on the way out. Okay, so is there anything to talk about? Assignment 2, yes, sir. Which one? Oh, right, because I forgot to upload the slides. Because I was hacking until like 2 minutes ago trying to make a demo. I'll put them up immediately afterwards. But I don't want people looking down on the slides anyways during the lecture. Any other questions? Yeah, I totally forgot to upload the slides before class. I was hacking. Anything else? Assignment 2 is sane. Hey, has anybody tried to run on late days? No? Really? Okay. So you have, the machines on Gates 5 are perfectly sufficient right now? So nobody's tried to run on late days? There's like a full set of instructions. Just do this, this, and this, and you're done. Yeah. Okay. All right. Okay. So let's go ahead and get started today. I feel like we should take a step back and figure out what we're doing. So we've been going pretty fast. We've been talking about a lot of information. You guys are all very busy with assignment 2, which is due on Wednesday. And so I just kind of wanted to tell you a little bit about where we're going in the course. Is that, so we've been talking a whole lot about how parallel machines work. We've talked about abstractions and programming abstractions that you'll use to write parallel code. And we've talked, like last week was kind of about hey, here's some strategies for writing some decent parallel programs. So this week, I think we're gonna, this week I think will be a little bit more relaxed. We're not going to talk too much about new stuff, but we're just going to make sure we understand what we already know. So today, I'm just going to go through a number of different examples of optimizing some programs that don't have to, that aren't this one grid solver. And so next time on Wednesday, we're going to talk a little bit about what does it even mean to perform well. We've only talked kind of about one metric of performance, which is speed up. And there are other ways to, when you're optimizing your programs, assess whether or not you're doing well. And so we'll talk a little bit about that next time. And then we're going to transition the course. We're going to transition the course back to some computer architecture. And we're going to start talking about how shared memory across a bunch of processors is implemented. And we're going to go into some architecture for about 2 weeks, which will bring you right up to the midterm exam. So the way the course is going to work is assignment 2 is due Wednesday. Assignment 3 will come out Wednesday or Thursday, like roughly around then. It'll be a new assignment this year. So we want to make sure it's tested as much as possible. And then that will be a 2-week assignment, and then that'll bring you right to exam 1. We do exam 1, and then you guys are off to spring break. So that's the lay of the land a little bit. But it does make sense that assignment 3 comes out really soon after assignment 2, so if you start taking late days on assignment 2, it's going to impact your assignment 3, and you can't really take late days on assignment 3 because if you're working on your assignment, you're not studying for the exam. So please make sure you're planning accordingly.
Can we get some more practice questions like we got in the quizzes?
Sorry? Well, we are giving you quizzes every 2 weeks, and those are previous exam questions. And I have a few other problems up my sleeve, and I could post a quiz on Thursday, for example. If Isha wants a quiz on Thursday. No, it certainly will not be an official quiz because we just don't have the grading horsepower to grade anything more than we already have. But yeah, we have a few more problems. Sure. Any other questions about what's going on these days? No? Okay. All right, so today, like I said, is a little bit more relaxed. We're just going to talk through some examples of what other people have encountered in parallelizing some programs, and they could be, hopefully they might be useful to you, maybe not in any of your immediate assignments, but perhaps in your final projects when you're encountering similar style workloads. So I dumped a bunch of examples on these slides. There's no way we're going to be able to talk about all of them. I just thought some of you might be interested in some other things that are down here, but we'll talk kind of about the first 3 or 4 of them today in class. Okay, and the assumption I think that's reasonable to make today is let's go ahead and assume that we're going to be working in a shared address space, just like all of your assignments so far. But everything we talk about today will be just as applicable if we're talking about message passing. So let's get started with the first example. And this is actually the application that grid solver example was taken from so far in the class. And it's actually a simulation of ocean currents. It's a large-scale scientific computing simulation where they're trying to simulate the flow of oceans. And they discretize the ocean into a 3D grid, which can be thought of as a sequence of 2D grids, where a 2D grid is a depth in the ocean. And we've been solving systems of equations, or we've been talking about a way to solve systems of equations on one of those 2D grids. So this grid solver example that we keep talking about was actually drawn from this larger application where we are simulating the time evolution of flow in the ocean. So the ocean is discretized into 3D space, and time is discretized into time steps. So in order to have a very high resolution simulation, we probably want a very small delta t, and we probably want really high resolution grids. And the first question in any application, like let's say that you wanted to do your final project on I want to do fluid simulation for the ocean, is you'll grab a piece of code and you should take a look at it, and you might ask, well, where are the major dependencies in the code, which is what we did when we first got started. And if you look at this application, this would be the block diagram of everything that happens in a time step. And every big box here is an operation on a grid, much like we've talked about. And all the lines are dependencies saying, okay, after you solve the equations on this grid, you pass the per element values to this thing, and then you do a per grid computation here, and so on and so on. And so the examples that we've been talking about kind of correspond to these two boxes in the program. The details of the program don't matter, but what you can imagine is that there's two types of parallelism here, right? There's all the data parallelism that we've been talking about, which is data parallel on a grid. And of course, if you wanted a little bit more parallelism, in some places in the application, if you look horizontally, there are boxes that don't depend on each other. So you could potentially perform all the operations in these different boxes in parallel. As you can imagine, since the grids are very big, the grids tend to fill the machine, and the implementers of this application said, you know what? We're going to serially process all the boxes and not exploit the parallelism in boxes that don't depend on each other. So all the parallelism will be the data parallelism that we've talked about in class. And you kind of know how this thing's been implemented, right? We know that we decided to spatially decompose the grid cells to processors in this 2D blocked arrangement. We also talked about decomposing the work into strips or interleaving the work. And we did arrive at this blocked arrangement. And why did we just say that this would be a nice way to go about things? Yeah.
Maximizes the arithmetic intensity.
And what do you mean by arithmetic intensity? Let's go ahead and define that just for a review.
It's the percentage of computation over the percentage of communication in a program.
Good. So we knew, exactly. So we knew that, like if we split up the grid into the processors in this way, we know that after every step in the process, every processor will need to kind of communicate its boundary elements to its neighbors. And so we were concerned, or not just, we were concerned that, it might take some time to do that communication. So let's try and maximize the ratio of useful work that we're doing compared to the amount of data that needs to be transferred between these processors. Let's minimize the amount of communication in the program. And hopefully we're doing math most of the time. And that's good. And then we also talked about, in the last 3 lectures, we talked about how we use barrier synchronization to sort of sync up all these processors after every phase. We talked about using locks to accumulate that global change variable every single time. And we talked about a few ways to sort of reduce contention on those locks. So in this application, so last time we talked a whole lot about working sets and memory access patterns. And in this application, it behaves exactly like what we talked about last time. There are 3 major working sets. One of the working sets are the input elements that you need to process every one output. Another working set is you'd like the entire, a set of a couple rows, 3 rows of the grid to stay in memory. or stay in cache. Because remember, if you walked all the way down to the end, you came back, if that working set wasn't in cache, then all of a sudden we would have to reload these values to process these. And if this working set didn't fit in cache on your machine, what was a solution that we used to try and also improve or to reduce the amount of communication that needed to happen? So we talked about this last time. So this first one's kind of a bit of a review. So let's say that these rows don't fit in cache. You wrote a normal piece of code for all j, process the elements. You get all the way to the end. You come back to row 2. Or let's just say you start here. And then you come back to row 3, and these elements aren't in cache. So what was a solution strategy that we talked about last time to improve the state of affairs here?
So instead of doing one line at a time, maybe do half or a quarter of a line.
So you will change the order, maybe walking in tiles rather than across the entire row. And why did you decide to do that?
So that you have better cache community, so that basically the row above you is still in cache.
It's still in cache. Yeah, so everybody remember that optimization from last time? And that's definitely something that we could employ on this example. Yeah?
Kind of very, niche, I'm going to say.
Niche. Okay. In fact, this niche optimization was something I did this morning on something else, just to let you know.
How common is to employ such methods?
Well, it depends if you care about performance.
I mean, do people, when they do high performance computing, sit down and see how was this for loop processed, how was it traversed, let's change this kind of?
Absolutely. So is matrix multiplication a useful thing to do? Hypothetical question. So this is I don't know, you did transpose in 213, right?
I'm going to do it tonight for the.
Oh, you are? Okay, good.
Matrix multiply is what I'm going to do.
So if you don't employ these types of techniques on a lot of dense linear algebra operations, which I think we would all say are fairly important, you're off even on, believe it or not, actually on a single core. You're off by 1000x of what you can do on a single core without parallelism at all, very, very quickly. Right, so the triple for loop implementation of matrix multiply versus the, presumably, I imagine Professor Bryant will have a six loop version of matrix multiply. And that difference on a single core, ignore CUDA, ignore parallelism, you run that on big matrices, it's 1000x difference on any modern processor. So these memory effects will actually swamp parallelism to a great degree for a long period of time. And then, of course, I wanted to point out that the last working set is the entire grid. And if the grid doesn't fit in memory and you're streaming it off disk, then we're in a completely different regime. And then we also talked about, this conversation up until now, we were talking about reordering the way that we walked over the data. And we also talked about actually reordering how the data is laid out in the address space. So in this example here, we just had this conversation assuming that if I have a 2D grid, I'm going to map grid elements into the address space in row major order, because I'm just going to call malloc on enough elements for a 2D array. But there's nothing preventing me from, and so that would be, if the data is laid out in row major order, then consecutive addresses are like these blue lines here on the left. But I could have just as easily laid out the data in block major order. I could say I'm just going to interpret matrix grid element ij, and I'm going to interpret it as I'm going to put that element in that appropriate address. So what I'm showing here on the left is I could easily have had consecutive addresses correspond to consecutive elements in a tile instead of consecutive elements in a row. I can write that code, right? And why may that be a good idea?
Cell is being computed in one core, locality.
Yeah, so if we're dividing the data up to work on this way, why don't we also reorganize it so all the data is right next to each other in memory that any one processor might access? So I like that answer, but I think we can get more specific. Why is that a good idea? so what, right? Like, okay, so that might, I'm liking where we're going. So how might spatial locality be improved by this way of laying out the data? Notice that I happen to draw this with six elements across partitions. Yeah.
So if you pull in the last elements from, say, for example, the first row of P1,
Yep.
and you're pulling in a whole cache line with say 4 elements, you might get cache hits when you do.
So say that again. I didn't quite understand.
So you would get the next 2 elements from the next row if you're pulling in the whole cache.
Ah, right. So right, exactly. So if I lay the data out this way, and the size of my tiles doesn't sort of map exactly right onto the size of my cache lines, then all of a sudden I'm pulling in the data that I'm working on is not contiguous in memory, and so near the edges of my cells, I'm going to have poor spatial locality and data access. I'm also, like more subtle effects, which we wouldn't really expect you to think too much about in this class, but it means as I'm jumping large page boundaries, I might be taking TLB misses. There's a bunch of other things that could slow you down as well if you don't have that spatial locality. And in fact, they did this, and they ran an experiment on a 32-core processor. So this is a pretty old processor, and these grids are of size 1K by 1K, roughly. And they ran this in a simulator where they can measure the amount of time spent doing various things. So this diagram is saying this is what threads 0 through 31 are doing, what all 32 threads are doing, overall throughout the program on one step or on a couple of steps. And they've broken the work down into the black bar, which is time spent waiting on data from memory. The gray bar, which is time spent waiting on other processors to synchronize. For example, barriers or locks and things like that. And then the bottom is the useful part of the program, is when the processors are actually doing math, computing the updates to the cells. So here on the left, this is the profile that you got if you laid out the data in memory this way. And on the right is the profile that you get if you lay out the data in memory this way. So what do you notice? First of all, what's the most salient feature of the graph? Which program is better? So you said the one on the right. Why is the one on the right better? It's faster. So we're good. So I mean that's important, is that it got done faster. Good? Right. So the next question is, well, why are we much faster? And this graph indicates that the working time is the same, which kind of makes sense, right? Because they're the same program doing the same thing. But the reason why the program on the right is faster is that it spends much less time for those processors to be waiting on memory. And presumably, they're not waiting on memory as much because of higher spatial locality or other memory access effects. Is there anything else that you notice about this program? Like, for example, if you saw this, would you be like, this static assignment, remember they used a static assignment of elements to processors. That's not very good. Maybe we should go do one of those things that we talked about in an earlier lecture, like dynamic assignment with a work queue, or maybe more advanced work stealing to make sure that the work is distributed well. Yeah. So you feel pretty good about this because all the processors are more or less running the same amount of time, but this is over the entire computation. So the actual thing that's telling you that the processors are actually running about the same amount of time is actually the size of that gray bar. Right, because they're all getting done roughly at the same time because there's a barrier at the end of the program. So they're all going to run about the same amount of time. The gray bar, so what do you notice between the gray bars? This is actually a more subtle thing, and now I'm just this is just conjecture. But there is a difference between the gray bars between the two, which is kind of interesting, right? So first of all, what's the difference between the gray bars? Sorry? The shorter on the right, which means that by improving the data layout, by changing the data layout, we reduce memory access time and we also reduce synchronization time. That seems unrelated. Let me go here first. Yeah, go ahead.
Because the blocks started operating more independently to each other.
Well, they were just as independent before, but things were a little bit weird with
Data.
yeah, exactly. So let me go here.
As a result, that they have to wait for everybody.
And I don't know the precise answer to the question, but do you want to add something? Yeah.
Yeah, because the arithmetic intensity is improved.
Is what?
It's improved.
It's improved.
Yeah,
Okay.
as we've discussed in last.
I would say it has. And how does that have bearing to the amount of communication overhead in the program?
Yeah.
So you guys are noticing some interesting phenomena. And like I said, I'm not sure what the right answer is, but I think you're right. I think the fact that we're taking fewer cache misses is kind of making sure everything stays roughly in more lockstep with each other, which means that they get out of whack a little bit less, and therefore when they hit those barriers in this solver, they don't weight nearly as much. But that again is pure conjecture, but the evidence points to that being the case in this example. Exactly. So those are some of the things that we talked about. So that's kind of like, well, the reason why we've been using this grid solver example is actually this ocean simulation. And this is similar to, for example, these days, I think big weather simulations might look more like this as well. So let's go talk about another workload, and that's what the astrophysicists like to do. So does anybody have a physics background at all in this class? Oh, cool. Anybody do anything like this? Because if you're in cosmology or astro these days, you may be doing some very, very large simulations. Do you know what this is trying to simulate? Yeah?
Is that how galaxies form?
Yeah, this is showing the time evolution of a simulated universe from, well, I guess that's not quite the Big Bang, because if it was the Big Bang, there'd be one dot. But as the universe ages, and you can see that gravitational forces are pulling mass together. And I have a little, like I couldn't find that exact video, but just to give you a sense, like here's the output of one of these things, and you can see it time evolved from the Big Bang, and then as the universe is expanding, you start to see mass starting to aggregate. And this is, I don't know what the answer is. I don't think they have it here on YouTube. No, they don't say. But I do know for a fact that some of the big astronomy simulations these days they will simulate the celestial bodies as particles. It's like a big particle system. And these things are using well above 1 billion particles these days. So just fitting the simulation in memory is one of the reasons why they use these big supercomputers, just so it could all stay resident. So you kind of see the structure emerging from. Okay, so let me push that down. And Keynote. Okay, and so there are many different algorithms for doing these kinds of things, but I'll give you like the canonical hello world if you decide to show up in the astrophysics community and I want to write one of these, is an algorithm called Barnes-Hutt. And like I said, there are many more modern techniques these days, but this is a good proxy for the way these things work. And the representation in the system is that every star is represented as a particle with some mass, and that the system is trying to simulate the motion of these particles due to gravitational forces. And so the gravitational force on, say, this star here, there is some force due to every other star in the simulation. Now, of course, if we did this naively, we would have an n-squared algorithm. For every particle, compute the gravitational force due to every other particle, accumulate forces, accelerate, and time step. Of course, if we're talking about 1 billion particles, an n-squared algorithm is pretty tough pretty quickly, right? 1 billion squared is not a regime that you want to be in. So the algorithm that they use is they say, you know what, gravity, it does have this nice property that its effect diminishes at a distance. So the effect due to faraway stars is significantly less than the effect due to massive close stars. And so the main approximation that they make is they say, you know what? We can agglomerate the mass of a bunch of faraway stars together and approximate the effect of all of those stars as one big star. So the main idea of these systems is, since the magnitude of the gravitational force falls off with distance, you can approximate the physics by aggregating or approximating the forces from faraway stars. And Barnes-Hutt is an n log n algorithm for doing that, which begins to make some of these systems tractable. And the main data structure in this algorithm is not a grid, but in fact it's a tree. So what I'm showing you here is I'm showing you a representation of the universe where every star is put in its own leaf node of the tree. And I've built the tree according to a spatial decomposition of the universe, where every leaf node of this tree has exactly one star. And in every interior node, we're computing the area, the volume, that's spanned by all of the stars, the child stars, as well as the total mass. So leaf nodes you can think of as particles that correspond to stars. Interior nodes correspond to the aggregate mass of all of the children. Okay. And if you want to compute the forces on each body, you actually just traverse the tree, trying to find all star, and you aggregate forces from every tree node. And you stop if the size of the tree node, the area that it spanned, or the mass that's contained in it, is small or far away, is small compared to how far away it is. So this ratio, size of the tree node L, or its mass, the mass of its tree node M, if that's small compared to the distance d, we're going to stop traversing down the tree, and we're just going to use the aggregate mass and aggregate position of that node as a proxy for all of the leaf nodes underneath. Right? So if all of the stars were really close, to check your understanding, we would, for every particle, we would traverse every node in the tree going all the way down to the bottom, like a depth first search, and aggregate all of the contributions of all the particles. But since the universe is spread out, many times we're going to stop traversal early and use the approximate aggregate mass of the whole subtree. And that's how we get to an n log n effect. So does the actual algorithm that's being, does that make sense? Because I think this will be important for us to talk a little bit about how it's parallelized. So you see how this is not an n log n algorithm at this point. People look a little confused, yeah.
But doesn't this mean that we consider a single star and the distance of everything?
Well, the algorithm is for every star, compute the forces. Yeah, for every star, compute forces. And if I didn't have this acceleration structure, it would be for every star, for every other star. Now it's for every star, walk the tree in depth first order, and stop if I get to a leaf node whose aggregate mass and size is small compared to how far away it is from the source star that we are computing the forces for.
So this will be n log n for each time step?
It will be, yes, yeah, for every time step, correct. Mm-hmm. Yeah. So on average, for every star, we're going to touch about log n nodes. Mm-hmm. And oh, yeah, sorry, so I actually have the pseudocode for you right here. It's for every time step, for every particle, traverse the tree to accumulate forces. Given all the forces, we can now apply F equals ma, compute an acceleration, and move the particle over the next time step. Make sense? So we have some challenges here now, is that the amount of work that we do per particle, per star, is very different. It's a function of how dense or how many other stars are around it. So if I'm in a big clump, computing the forces on a star is going to be very expensive. If I'm a star way out at the fringes of the universe and nothing's by it, it'll be very, very cheap. And moreover, that density is going to change over time, because you saw in the video, it started very uniform in density, and then the density got very irregular as the universe evolved. So there's a little bit of there's some trickiness here. So given that, how would you think about trying to figure out how to divvy up work across a bunch of processors? So you now have the rough pseudocode of the algorithm, you've looked at it, And imagine on assignment 3, I gave you a challenge of trying to parallelize Barnes Hut. So where do we get started? I'm going to go over here. How would you get started? And again, like, let's think about, let's do the simplest thing first. Yeah.
Make let every core compute the gravitational force
Of a different set of stars. Absolutely. Sounds like a great place to start, right? Simplest possible algorithm. And you're going to run it. And you're going to get some speed up. And at some point, you're like, I want to do better. Because let's say that the problem you have is that, well, different stars have very different costs. So this is one of those examples where it's kind of hard to predict how expensive a star is going to be. So I interpreted your first answer as let's just statically assign stars to processors. And I said that's an outstanding first answer. But now let's say what happens if we want to do a little bit better. Yeah.
I would assume that in some patch of the stars that's close by, and then there's another patch of stars far away. They both see each other as like large single blobs. So let's say we have like n number of stars at one patch, and those n number of stars can share one computation of gravitational force for this patch B over here.
Okay,
And
makes
you can
sense.
save on computing that again, traversal of the tree maybe.
So you're changing the algorithm even further, right?
Kind of.
Right. Okay, and that might be perfectly fine because we've already approximated things. So you may have another better approximation. But let's say for the sake of the next 2 or 3 minutes, let's not change the algorithm any further than I've already changed it. I gave you this program. I said, here, start parallelizing it. And the first answer is static assignment of particles to processors. And I say that's absolutely the right first answer. And then I'll say, well, hypothetically, let's say that you observe significant workload imbalance due to that assignment. Yeah.
We could have some kind of cues such that if say one particular star has traversed and finished working earlier than another, then that
For one processor, yeah.
Sorry, then that processor would be free, so it could grab work from another star, which may have to like traverse more deeply.
Sounds reasonable. So so I'm going to interpret your suggestion not in terms of an elaborate work-stealing scheme. How about just we're going to divide the stars up into smaller groups, and we're going to throw all those groups in a work queue, and every processor will just take the next group available when they're done, and that would be another fairly useful solution. And that I would try that next, and I would measure it, and that might be fine. They went with a different approach actually in this algorithm or in this application. And I'm curious to see if anybody has any other ideas, because everything so far that's been said is great.
Is it possible to like calculate the number of particles in each box?
Yes, because the tree has it. So you have that information. I can give you that.
That you assign each processor like the number of like soft. If one of them is really dense, you just allocate probably the one processor.
Okay.
And if you have like very sparse one, you give it to like you give a few boxes to like one processor or something like that.
So you're saying that, okay, so we went from pure static assignment to, well, just figure it all out at runtime with the dynamic queue. And you're saying, well, maybe we don't have to because we actually have some information about how expensive stuff's going to be. So let's just have the tree tell us how expensive stuff is going to be, and then I'll statically assign things. Is that a reasonable summary of your approach? But these particles move. Right, so the number of particles in a box, the tree is changing frequently because the particles are moving all over this place. So I like your solution. Yes?
So we statically assign for like a bunch of time steps and then reassign because it's not like the particle moves that much.
The universe doesn't radically reorganize itself every time step. And so your solution, if I did this at one point, probably would hold for a while, right? And so exactly, so that's exactly something that they chose, is they actually used a semi-static approach, like what you guys are suggesting, which was the reaction to the first approach, which is what other folks suggested. And so for every time step, every processor is just tabulating how much work it did for every particle. So for every particle, I have how expensive it was in the last time step. And then when I'm building the tree, I can just compute for every node how expensive all the particles underneath it were. And now I know how expensive every particle is. And then I just have to divide those out, or I have to partition them out to all the processors. And every once in a while, I'll reorganize things. Every once in a while. So let's finish this. How do you, okay, so given we have the cost for every particle, how are you going to finish the proposal, the sketch of the algorithm that you guys suggested? How are you going to actually do the division onto the workers? Let's go ahead and finish off the. Yeah.
I have some idea of the total amount of work, so you can calculate how much work each processor would do in the ideal case.
Mm-hmm.
And so you could just greedily assign the most expensive operation to one processor and do that to get some sort of estimate or some approximation of the optimal.
And are you going to do this serially, and then just like assign work to people, or? Let's think about so that sounds good, like a good solution. So remember, the supercomputing simulation is now running on that thing with 200,000 cores in Titan X. So, I think it's a reasonable first start to say, look, it's a big, expensive supercomputing simulation. Hopefully, I can add up a bunch of numbers in a tree, not too quickly, and then I'll just distribute the plan out to everybody. What they actually did was something slightly different. Is that they decided to duplicate work. They said, we want to avoid communication at all costs between processors. And we know everybody has access to the amount of work that every particle did in the previous time step. So to avoid any overhead of communication, they have every processor just compute in parallel redundantly this distribution, much like what you were suggesting. And then every processor knows that if there's total amount of work W, I'm just going to take the ith W over P packet of it. And the way it did that was it says, I'm going to take the subtree, I'm going to walk the subtree in depth first order. And I'm going to find the first subtree, and I'm going to just keep counting up how much work is in all of these subtrees until I get to I times W over P. And then I'm going to take the next subtree. And so this is actually a pretty cool algorithm. So first of all, we distributed the work without any communication. And there's another interesting property about how it was now assigned to the processors that's actually very, very cool. Imagine if we had a work queue, and imagine that we were okay with synchronizing. And every thread, whenever it got done, it just took the next item from the work queue, the next particle from the work queue. That's not what's going on here. This is actually a static assignment where I'm just breaking up the tree and giving the tree to different processors. So why am I saying this is cooler?
There's no synchronization.
There's no synchronization, good. And there's actually even a much bigger effect here, which actually goes back to something you said earlier in class about, hey, if this particle is close to this particle, maybe we can reuse some computations in accessing these guys far over there. Yeah? Each processor is working on stars that are really close to each other. And stars that are really close to each other are going to essentially have the same neighbor lists. They're going to visit the same parts of the tree. So that part of the tree is going to end up in that processor's local memory, in its various caches and things like that. So if you think about it, if I had to process this entire subtree, I'm going to descend basically to the same distance in every single one of the nearby, when computing every one of the particles that I own. And so I'm going to have extremely high cache locality in accessing all these neighbors. Yep.
This tree is built for every single star at every single time step, right?
Well, you could rebuild the tree occasionally. You could use the same philosophy that you guys said, hey, the distribution changes slowly, so we're okay with making the tree get a little out of whack, and we'll do it periodically.
On a high level.
But on a high level, it's continually being re-updated, yeah. So the nice thing about this is by this really smart work distribution policy, they actually don't care at all about memory layout of this tree. What they end up doing is they just randomly assign particles to different parts of the address space. They make sure that every particle, every processor works on very, very close to each other particles. And just by the nature of the computation, the appropriate particles from the data set get loaded locally into cache. And so there's extremely high cache hit ratio in this application. So they don't care at all about data distribution. It was all completely about how to assign work in a really smart way. And that was cool. That was cool. In fact, so I put a... So this was the graph. We'll jump through the text. This is the same graph between randomized assignment, which I would think of as randomized assignment in this case would be the next available thread takes the next item out of the work queue, versus the cost zones assignment on the right, which is the smarter assignment that I was talking about. And what's the big salient feature here in this graph? So the one on the right is better. It's a more performing algorithm. And why is it more performing? Sorry? Because of data access. Interestingly, like random assignment is actually going to give you pretty good balance because there's so many particles, and if you just take the next one and you just take the next one, we're all going to finish roughly at about the same time. The assignment was actually a locality-aware assignment, and that was the real reason for the big performance improvement. Yeah. It's a good question. Why do you think there's more work? So I think there's two interesting questions for those who have a critical eye. Is why is there more work on the right, and why is there? I mean, it's almost like there's more variance in synchronization time, actually. So why do you think there's more work?
I think the more work is due to each of them traversing the tree to find their place.
So the more work was actually the work of computing the assignment. So you end up doing a lot. You do more work, but it has a payoff because it shrinks that black bar a whole lot. Exactly. I have no clue why it seems like there's a lot more variance in synchronization time. I couldn't tell you that one, actually. So I'm open to anybody's suggestions. Cool. Yeah. Okay, so those are two examples. We can do some more. Here's one that I was working on this morning. And so I think if Professor Bryant is going to do a lecture on data locality, I think this is a good example. So here's something I needed to do this morning, actually. Is I had a student that needs to compute, given an input image and a database of 100,000 images also taken from around campus. The student needed to compute what images in our database are closest to this. Right? And so what I'm drawing on top of the image actually is gyro showing where the camera moved after being in this position. Because what the student is trying to do is the student is trying to say, hey, if I had a GoPro on my head right here, and I match this image to a huge database, and I have history of where people walk associated with all these images, I can just transfer that information and make a prediction about where I'm going to walk, given what I'm seeing now. So very, 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 very basic computer vision usage. And this is another example of where here's the query, and believe it or not, this person did have a GoPro stuck to their head. These are all a bunch of images that he has seen from around town. Notice that the nearest matches are a bunch of intersections, but not necessarily the same intersection. And so in this case, the system is properly predicting, hey, look, yes, you are going to go to the right. And here it is predicting, hey, you're probably not going to move because you're standing at an intersection. Anyways, that's not the point, but that's the reason why we wanted to find the nearest matches to a bunch of images. And these days, the way you do this, if you want to be really naive, is you'll take the image, you'll turn it into some feature representation. And in this particular case, it was evaluating a deep network to get out a feature vector. And then we're just going to do a very, very simple comparison of the feature vector to a dot product between two feature vectors to compute how close things are. So the distance is just the inner product between these two vectors. And the vectors in this case were about 10K elements, about 9K elements. So we wrote this code right here. For all images that I wanted to run in query, for all images in the database, just compute the distance. Makes sense. So no fancy indexing, no trees. Probably should have used something like that, but I didn't. And so I was trying to speed this up. And so first of all, does this sound okay? Like, does anybody see any performance problems with this code? You can't change the algorithm. I'm not going to move to a fancy algorithm here. Just straight up systems programming. Any problems with this code? You've seen code that looks awfully like this. Yeah. Did I? No, that's fine, right? No, I'm running right across completely. Yeah, that's fine. That one's fine. Is bandwidth an issue? So what do you think? It's well, yeah. I just wanted to tell you that the database is big. You know, the database will not fit in cache, and this code iterates over all 1.7 gig for the first query, and then comes back and iterates over 1.7 gig for the second query. Yep. So do you think bandwidth's an issue? I mean, just because the data set is big does not imply that bandwidth is an issue. It implies that the bandwidth may be an issue. What do you guys think? Yeah. Yeah. So yes, sure. I could improve this by a factor of 2 by memoizing that result. Yeah, by only computing the triangle. Exactly. Yes. But I'm really worried about bigger effects. Yes.
Why are we sequentially computing the images?
So how are you going to parallelize it?
Do something like silk.
Yeah, I mean, I could parallelize over this loop. I could parallelize over this loop. Which one do you plan on parallelize over?
First of all, I would parallelize over I.
Over I, the outermost loop?
Yeah, because doesn't the outermost loop traverse over like a single image and then compares that single image to all?
Well, this is over all the queries. A lot of queries. So just you can imagine I have a bunch of queries I want to give you. This is a database. Query, 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 query. And then to satisfy a query, I'm just looping over all images in the database.
Just like let's do the innermost loop.
Okay.
And do that in parallel.
Okay.
Do each of the computations in parallel.
Good. Okay, we can parallelize that. What do you think is going to happen? Have you seen this code before? This is exactly assignment 1, problem 5, right?
And also, you're going through the entire database, queries number of times.
Yep.
Why would we do that when we could just go through the database once? And then
Well, what if I have more queries than database size? So, but I see your point.
it's going to be less likely just because like your database is supposed to be information that's useful for your queries. So you get more queries than databases. Then, like I guess that might happen when you're building the database, but after your database has been built into a research, that's probably not very likely.
I mean, you could argue that Amazon gets more queries in a day than it has products in its database. So, but in this case, okay, fine. Okay, so you're saying that there's not going to be very many queries. So you're saying reorder the loops?
Yeah.
Okay. I like it. So let me show you what I did. I basically did that, but I didn't completely reorder the loops because there are a lot of queries. And remember, every one of these queries is 10K times 4 bytes. It's already a 40K vector. So as soon as I'm running 10 or 12 queries at once, I'm already blowing out my L2 with queries. So all I did is I basically took you guys' suggestion. I realized that this code was bandwidth bound. And so I added another loop. I decided to say, you know what, let's batch our queries and do 8 of these queries at a time. Let's do 8 of these queries at a time. And it worked a whole lot. So why is that a good idea? So it was bandwidth bound, but how did I increase the arithmetic intensity of this application? Yeah. So I decided to take 8 queries at a time, so about 80 kilobytes of data, which fits in L2. And then I'm still streaming over the entire database for all images in the database. But now at least every time I load a value from the database, I reuse it 8 times over my 8 queries. And so I have batched my queries into a subset of the data that fits in the L2 cache, and a database that I'm streaming over that at least every time I load it in, I reuse that value 8 times. So I increase the arithmetic intensity of my program by a factor of 8, while not blowing out my cache for the data that's supposed to sit there anyways. So that's the reason why I couldn't go all the way with my queries. I had to be careful. And so this was really effective. I want you to ignore the non-batch data point, because the reason why I was rushing to class was I was trying to verify these results. And on my way to class, I have identified that they were not correct. I've thought of, so I'm going to update this slide. But what is absolutely correct are my batch performance, which you can see that I'm still bandwidth bound, actually, out to 64 threads. I'm only getting a 16x speed up. But the blue number is going to be quite a bit lower. And I'm going to update these slides. But the reason why you didn't have a song before class is because I was like, something is wrong here. I should not be seen. So here's an interesting question. What told me that my result was wrong, that I had a bug in my non-batched code? The batch code is correct. This is the scalability, and that's the throughput. There should be something that tells you that there's a bug in my non-batched code. Yeah.
If your throughput is higher for the batch, why is your speed up higher for the non-batch?
Well, that could be, that's not necessarily, I could have a very slow single-threaded implementation in the non-batched case, which could make it much easier to speed up. And also, the whole computation would get much slower. But if you think about what I did to my program, what did I do? I increased the arithmetic intensity, which should make things much faster on one core. And what about its scalability to multiple cores? What do you know from assignment 1? It should not have good speed up here in a bandwidth-bound application, because like 1, maybe 2 or 3 cores should saturate memory. And I saw this. And so I was sitting there at my desk trying to figure out why that was happening, and then I found the bug in my code right before I left. So I'll get this fixed. But this was a case where theory was actually telling me that I had a bug without knowing that I had a bug. So we'll see if theory meets practice when I fix this bug after I go back to my class. Okay, so that was one example. Let's go, yeah?
So that full operation could be modeled as a matrix multiplication?
Absolutely.
With doing that, could you get better speed up?
If I just said call matrix multiply?
Yeah.
Yeah, I very well could have, but guess what? How matrix multiply is implemented under the hood. Exactly those kind of techniques, and you'll see that tonight at the recitation session, actually, at the review session. So how about we talk a little bit about parallel scan? Everybody knows what parallel scan is, right? Everybody loves parallel scan. So we know, I don't even have to define what the scan primitives are, because you know this very well from assignment 1. And I want to talk a little bit about an exclusive scan today. And as you know, I could implement an inclusive scan like this. So you know this from 210. What is the work complexity of this algorithm? So this algorithm is going to pair up. In the first step, it's going to pair up everybody. The second step, it's going to pair up everybody. So this is not the algorithm I gave you on your homework, right? So what's the work complexity of this algorithm? Just to review. Sorry? N? Sorry? The amount of work by 213 definition, right? 210, sorry. How much work is there? Does O of n work in the first step? Obviously. slides everything over in the second step. I guess this one might be harder because you haven't seen a bad version of it yet, have you? Not quite n squared. How many steps are there? Log n. And it's doing n work per step. It's your n log n naive parallel scan. Exactly. And its span is log n because there are n squared steps. Log n steps. Sorry, I'm having a rough day today. But this is the version that you guys have learned in 210. It's the version that we gave you on assignment 2. And this one has total work n as well as span asymptotically still log n, right? But in this class, we kind of care about the constants. So what are some of these constants? Sorry? Well, the span, yeah, is pretty obvious, right? Because I have log n steps in the upsweep phase. And I have another log n steps in the downsweep phase. Exactly. And, we could argue a little bit about what's the constant on the work. But, we can start adding things up as well. There's an add there. There's a copy there. There's another add there. Back of the envelope, you could think about it as maybe 3. So what if I gave you the task of implementing a parallel scan? What if I gave you that task? But what if I gave you that task on, let's say, a CPU? And maybe a 2-core CPU? Where the only parallelism we needed were 2 cores worth of parallelism, 2 threads. So what do you think about the algorithm now? I mean, it's a really nice algorithm. It's a very, very famous algorithm. And so imagine that we said that, like a logical thing to do is be, say, P1 is going to do this. P2 is going to do the other side. Would you just copy and paste the code right into C++ if I asked you to write a parallel scan? Yeah. Yeah, there's one message, so there's not a lot of communication between the processors. So that's good. I like that. Anything else? Somebody should go try and write this code actually on a CPU these days. So what about the locality of data access? It's pretty local in that this stuff is over here and that stuff's over here. That's good. But what about within a core? You're kind of bouncing all over the place every step of the way, right? Right. Your spatial locality of your cache lines is not going to be particularly good. And remember, you actually also just took a constant on the number of steps as well as a constant on the amount of work that you were doing. Because what's the work complexity of the actual algorithm on 1 core? Sorry? On 1 core? So if I give you, if I asked you to do a sequential implementation of scan, yeah, you're just going to, for I equals 0 to n, you're just going to write the code, right? So this code is now running on 2 cores. It's bouncing all around through memory and increased work by kind of 3x. So something is a little bit amiss. So if I gave you 2 cores, how might you do a scan? Well, you could use 1 core, but I'd like you to use 2. Imagine you have plenty of bandwidth and things like that. But how would you do a scan? Imagine you've never taken this class before. Imagine you've never taken 210. And you didn't even know about this algorithm. Just how would you do it off the top of your head? Yeah.
Separate scan on each one, so just a linear scan on each and then.
So you just be very simple about things. You're like, okay, I'll take the first half of the list. You take the second half of the list. And then when I'm done, let's go ahead and split up, adding the base pointer to the second half of the list, right? So here, that's what I do. P1 does its sequential scan. P2 does its sequential scan. And then, of course, the final element computed by P1 needs to get added to all of these guys. And we can just parallelize that and do that completely in parallel at a work complexity with a constant of 1.5 on it, right? So that's pretty good. So now I have a perfect access pattern through memory. And I have this work complexity of 1.5. Yeah, exactly. Have you ever thought about how to do a scan on a SIMD width amount of data? Imagine if you were doing a scan with AVX instructions. You had to scan 8 things. Or imagine on the GPU you had to scan 32 things in a warp. That's a parallel scan. Have you ever thought about how to do that? So take a look at this code. This is some CUDA code that we wrote. Well, in fact, actually, the NVIDIA folks wrote it, and I copied it. And so this is a CUDA function that performs a scan on a warp's worth of amount of information. So it uses 32 threads to perform a scan on the 32 elements in pointer. So can somebody tell me what this code is doing? And remember that diagram I put up there at the beginning of the of this segment. So look through this. Think about how CUDA works now in your head. And what is this code doing? And even though the text is on the slide, it's actually a pretty nasty little piece of code to think through what it's doing. So does anybody want to try and explain it? Yeah.
It is basically dividing, like modeling the different lane of the vector. Like,
Mm-hmm.
for example, if you are the first vector, so what you're going to do is just add the first two together
Yep.
and reverse them.
Uh-huh.
And you can imagine the whole process of developing as a pyramid. The reverse pyramid, and in the first layer there are like the most work to do, and the second layer there are like half of the work to do. So if your lane is like the last one, what you're gonna do is like you will do the most of the things together. And in total, they will perform all the computation that.
Exactly. So let's just read through the code. So in the first step, remember this is a scan of width 32. The first step, every thread will just completely in parallel, because every thread in a warp executes in parallel, just accumulates the 2 adjacent elements. And the next step, you accumulate 1 step away. And then the next step, you accumulate 2 steps away. And then 4 steps away, and so on and so on and so on. So what's my span? What is log n, log 32 specifically in this case. 1, 2, 3, 4, 1, 2, 3, 4, 5. And what's my work? How much work do I do in the first step? N. How many steps do I have? Log n. I basically do n work every step, right? So my total work is n log n. So why in the world are we not using this really nice, work-efficient parallel scan here? So first of all, in CUDA, how many instructions would this take? How many clocks would this take? 5 clocks, right? Every single line of code is, let's ignore the branch, is 1 instruction. So it takes 5 instructions. What happens if we implemented the work-efficient parallel scan? How many instructions would it take? Somebody said 10? Sorry? 32 instructions? I mean, 10 is actually we might be getting rid of some constants here, but you know that you have to do log n steps in the upsweep and another log n steps on the downsweep. So it's going to take 10 instructions. So the work-efficient parallel scan is twice as expensive in this system than the work-inefficient parallel scan. So why is that the case? So if all of the lanes, or all the threads in the warp, if they just don't do something in that clock, that's just wasted work. And so in this particular case, choosing the algorithm with the minimal span is much smarter to do than choosing the algorithm with the minimal work. So this works on 32 elements. What if you wanted to compute a scan of like something bigger in CUDA? How would you do it?
Divided into chunks of 32.
So you divide it into chunks of 32. And you can use this as a black box to get really good partial scans. And then what would you do to combine them?
Run them on each warp and
You can store the sum of each block
Uh-huh.
and then basically add the sum of the previous block to the next block.
Yep, and which is what I did in the 2-core version of it, right? Right, so notice what I'm doing here is I'm building up only as much parallelism as I need. And at every step in the machine, I'm choosing a different algorithm that is appropriate for the size of the cache or the execution characteristics that I have. So I like this idea. Is I just told you how to take 2 sequential scans and stick them together to make a 2-wide parallel scan. I just told you how, given a warp on a SIMD machine, how to do a scan of a warp size amount of stuff. And so imagine if I had 32 blocks of 32 or 32 groups of 32. I could use a warp to do all of the piecewise 32 element scans in parallel. I would then have 32 partial scans. And then I could use my 32 element scan to do a 32-way merge of all of the partial results. So now I have a scan that works on 32 squared elements or 1,024 elements. That's pretty cool. Right? And that's actually, this is exactly the code that we gave you if you want to use. You don't have to use it in your assignment. To do a really fast in shared memory scan on assignment 2. That's exactly how it works. Is every warp does a partial scan, and then we use one warp to combine the results, and then we add the partial sums back out to all 32 things. And just for those that are interested, that's kind of what it looks like. We do all the partial scans here, all the threads in the thread block barrier to wait for all the partial scans to be done. Then one thread, the threads only in warp ID 0, perform the block scan. And then all the other threads, other than the warp 0 threads, end up accumulating the partial results, the appropriate partial result, into their system. Highly, highly machine specific. And then, of course, if I wanted to do, that was a 1,024 element scan. If I want to do a much bigger element scan, then I start doing the same thing at the level of the thread blocks. So I do a warp scan inside the block, combine the various warp scans, generate partial sums per thread block, and then I have another thread block come through, merge all those, and so on and so on. So I can just keep building this up. And you can imagine if you want to do a scan over a 30,000 GPU Titan machine at Los Alamos, at Oak Ridge, you might build up a scan in this sort of way. Cool. Yeah. So the point here actually is that notice that I'm using a different strategy at every level of the machine. And I'm being very careful to only create as much parallelism as I ever need. Because parallel algorithms tend to introduce constants on span or work. And I'm trying to avoid that as much as possible. I'm only doing parallelism like on the block scan and those kinds of things. Okay, so let me finish up by talking about one other. This is a little bit more of a cool algorithm for those of you that like scan. Does anybody know what a parallel segmented scan is? Did you guys do that? I hope you didn't do it. It's still my thunder. No? So segmented scan is a great algorithm, to work data parallel in situations where you have very irregular data structures. For example, a list of lists. So a list of lists can come up in a bunch of different places, such as a list of circles that overlap a tile. But this is not meant to be a suggestion for the assignment, by the way. Or in Barnes Hut, a list of all particles that may impact a particle in the simulation, because that list is different for every particle based on density. Or in graph-based algorithms, you can think about the list being a list of vertices, and the list of lists would be for every vertex. Here are a bunch of edges touching the vertex. And so the lists, the sublist, will be very different sizes. Okay? And so you notice that there's actually 2 levels of parallelism in a lot of these applications. It's parallel over the outer loop. And often you can also be parallel over the inner loop at the same time. And it's very irregular. So segmented scan is, imagine we had a list of lists. So now instead of the sequence A, I have a sequence of sequences, if I want to use the terminology for 210. And segmented scan is going to take this list of lists, which is encoded as a sequence, and flags that indicate the starting point of all the sublists. So here, this sequence 1 through 8 is actually two sequences, 0, 1, 2, 3, as well as the sequence 4 through 8. Okay? And I've encoded those subsequences simply just by putting a bit here in a companion list. Does that representation make sense? Okay. And a segmented scan is going to perform a scan individually on each of the sublists. So scan would have produced the total scan. Segmented scan will produce 1, 3, 6, and so on and so on. And then start over again, right? It'll be 4, 9, 15, 22, and so on and so on. And since we're not completely out of time, but segmented scan actually surprisingly looks a whole lot like the work-efficient parallel scan. There's only one difference, which is this conditional here. If the flag is 0, do something else, do something else. And you'll see this if flag and if flag here in the algorithm. So I'm not going to spend a lot of time explaining this code. It's just something fun to look at on your own time. But I can give you the gist of how the algorithm works. So these flags are like the starting points of the various lists. So as we're performing scan, you never want to accumulate data. You never want to move data across one of these flags, because the scan of the previous sequence should not impact the scan of the current sequence. So if you look at the downsweep phase, it's behaving just like the downsweep phase of regular scan, except whenever there's a flag bit set on one of the left inputs, we don't accumulate that into the output. So there's a flag bit set whenever the left input corresponds to a subsequence that contains a break in it. So you can see how that's the reason why we don't want to add that information over, because we might be accidentally contributing information from one sequence into the next subsequence. And so, and we can go back to the code. If you look at the upsweep, it says, if the flag is 0, we want to sum the two operands into data. And if the flag is 1, we do not sum the operands in. And notice that the resulting flag is the union of the flags of the two operands. So these partial sums are basically holding a flag which says, did I come from two things? Or did I come from a starting position? I want to know that. And if I did, I'm never going to accumulate into the other side. And the downsweep is a little bit more complicated, but also respects those flags. So let me tell you why I'm telling you about segmented scan, just really quickly. We'll use it in an application. Imagine you wanted to multiply a matrix times a vector, and that matrix was sparse. So here's a sparse matrix. Most of the matrix is 0. So we could represent this as a dense matrix, but it could be very, 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 very large. Very, very large dense matrix. Imagine that most of these elements are zeros. So a common way to store a sparse matrix is to simply store the non-zeros. So here is a representation of that matrix. I'm going to store all of the non-zeros, the numbers 3, 1, 2, 4, 2, 6, 8. And then I'm going to store extra information for the column that every non-zero is in. And I'm going to store the starting point, the index into this array of every row in the matrix. So this says that row 0 starts at index 0. Row 1 starts at index 2, which means that row 0 has 2 elements in it. Those elements are 3 and 1, and they're located at columns 0 and 2. So you can see how I've built up. I'm representing a sparse matrix as a sequence of sequences. And the row starts, these are the indices where the flag bits might get set, if I'm representing this as a scan. So if I wanted to multiply this vector times this matrix, I now can do that multiplication using two very, very simple parallel operators. Is I can map all of the non-zeros against, so I compute the products, which is a sequence, which came from the non-zeros, multiplied by x gathered by the column ID. So this is the gather, this is the map, and the output is just a per element product on those two sequences. So now I've multiplied every non-zero in every row completely in parallel against the appropriate element from the column vector. And then if it's a matrix multiplication, I just need to compute the sum of every row, which means I can run a segmented scan given this data structure right here to compute the sum of the products, which gives me these. And then if I just take the last element in every segment, that is the resulting vector of the sparse matrix multiplication. So this has allowed me to store a sparse matrix very efficiently as a single sequence and an extra set of flags, and allow me to perform matrix multiplication as one big data parallel operation, this parallel segmented scan, regardless of any differences in the number of non-zeros per row. Yes?
The speed up that you're gaining, wouldn't you lose that? Like, if you have issues with trying to maintain the lengths to be a power of 2? Like, even in segmented scan examples that you showed, the sequences you showed had to be of length power of 2.
That's true. The simplest implementations always just round up, which can cause you some problems. But the benefits you could get from parallelization actually sometimes can outweigh that. But I think I agree with your concern that the overheads of coming up with very, very wide parallel algorithms often are concerning. For example, we talked about memory access patterns, extra span, maybe rounding up to powers of 2 to keep the code clean or something like that. Yeah, those are all there, and so there's things that you have to think about. But I did think I wanted to throw segmented scan in here because if you didn't have it in 2.10, it's a very, very valuable primitive that can be used in many situations, and especially, for example, on a GPU where you have to have so much parallelism. If you look at the Thrust library, they have very fast implementations of segmented scan. Now, they're going to be implemented much more like this than they're going to be implemented like this. But it's a useful primitive to have. OK, well, those were just some examples. Just to kind of, I threw some stuff in here on parallel ray tracing, which people that have taken my class already know. Just some fun examples of the way people think about these problems.